Assalamualaikum and good morning everyone. So now let's jump off to the baseline chemical profile for our comparative analysis. We are examining two correlation complexes, Hexaaquacobalt and Hexaamminecobalt. Looking at the central metal, as the similarities of both complexes utilize a cobalt transition metal core in the positive 2 oxidation state because neutral cobalt has 27 electrons. Losing its 2 valence for s electrons leaves us with a 3d7 electron configuration. This makes both of them active d7 systems. In terms of physical architecture, both exhibit a coordination number of 6, meaning they adopt a classic octahedral geometry. The only true variable here is the type of ligands present. Both water and ammonia are neutral monodentate molecules that bind via their lone pairs and sigma donors. However, while water is a classic weak field ligand, ammonia acts as a significantly stronger sigma donor. This fundamental difference in ligand types will form the basis of how we calculate and compare their splitting characteristics using crystal field theory and molecular orbital theory.
Next, I will explain about the crystal field theory analysis for the complex hexaaquacobalt ion. In this complex, water is neutral ligand, so the oxidation state of this cobalt is +2. Therefore, cobalt 2 plus has a 3d7 electronic configuration. According to the crystal field theory, when 6 water ligands surround the cobalt ion in an octahedral arrangement, the 5 regenerated d orbital split into 2 energy level, which is 3 lower energy T2G orbital and 2 higher energy EG orbital. The energy difference between these two sets of orbital is known as the octahedral crystal field splitting energy delta O. Since water is a weak field ligand, it produces a relatively small delta O. Electron maximizes the number of unpaired electrons by singly occupying all available T2G and EG orbital before pairing begin. Therefore, the d-electron arrangement is T2G5 EG2, giving a high spin complex with 3 unpaired electrons that indicate paramagnetic. The relatively small delta O also means that the complex absorbs lower energy, longer wavelength visible light for the DD electronic transition, which contribute to its characteristic color, which is pink.
While the previous complex, Hexaaquacobalt ion, contains the weaker field ligand H2O, this complex contains NH3, which is a stronger field ligand. This allows us to observe how increasing ligand strength influences the crystal field splitting and the properties of the complex. First, because ammonia is a neutral ligand, the oxidation state of cobalt in Hexaamminecobalt is 2+. Therefore, the central metal ion is cobalt 2+, which has a d7 electronic configuration. According to the spectrochemical series, ammonia is a stronger field ligand than water and therefore produces a larger crystal field splitting energy. In an octahedral complex, the 5 degenerate d orbitals split into 2 sets of orbitals, which are the lower energy T2G orbitals and the higher energy EG orbitals. However, even though the crystal field splitting energy is larger, it is still smaller than the electron pairing energy for cobalt 2+ ion. As a result, electrons continue to occupy the higher energy EG orbitals before complete pairing occurs, giving a high spin configuration with an electron arrangement of T2G5 EG2. This configuration contains 3 unpaired electrons, so Hexaamminecobalt ion is paramagnetic and will be attracted to an external magnetic field. Finally, the larger crystal field splitting energy means that more energy is required to promote an electron from the T2G orbitals to the EG orbitals. Consequently, the Hexaamminecobalt complex absorbs higher energy shorter wavelength light than the Hexaaquacobalt complex. Since the observed color is complementary to the light absorbed, the two complexes exhibit different colors. Therefore, although ammonia increases the crystal field splitting energy, the Hexaamminecobalt complex remains a high-spin paramagnetic D7 complex with 3 unpaired electrons.
Crystal field theory explains that ligands split the d orbitals into T2G and EG sets in an octahedral complex. However, CFT does not fully explain why different ligands produce different magnitudes of splitting energy. Molecular orbital theory provides a deeper explanation by describing the orbital interaction between the metal ion and ligand. In octahedral coordination complex, the 6 ligands donate lone pair to electrons towards the central cobalt ion through sigma bonding. The metal orbitals involved in sigma bonding are the 4s, 4p, and EG orbitals. The ligand lone pair combine to form ligand group orbitals, also known as LGOS, which interact with metal orbitals of matching symmetry to form molecular orbitals. The EG orbitals experience the strongest interaction because they point directly toward the ligands. This causes EG antibonding orbitals to rise in energy. Meanwhile, the DXY, DXZ, and DYZ orbitals do not point directly toward the ligands, so they have a little overlap with the ligand sigma orbitals and remain approximately non-bonding in sigma-only complexes. When the ligand group orbitals interact with the metal orbitals, bonding and antibonding molecular orbitals are formed. The T2G orbitals interact weakly in sigma-only bonding, so they remain nearly non-bonding. However, the EG orbitals interact strongly with ligand sigma orbitals, forming high-energy antibonding EG orbitals. The energy difference between the non-bonding T2G orbitals and antibonding EG orbitals correspond to the octahedral crystal field splitting energy. This shows that molecular orbital theory explains the origin of crystal field splitting through orbital overlap. Both H2O and NH3 behave primarily as a sigma donor ligands. Neither ligand is a significant pi donor or pi acceptor, so the bonding in these complexes is dominated by sigma interaction. However, NH3 is a stronger sigma donor because nitrogen is less electronegative than oxygen. As a result, NH3 produces stronger orbital overlap with the cobalt, raising the energy of the antibonding EG orbitals more significantly. This leads to larger splitting energy in hexaamminecobalt than in hexaaquacobalt. Larger splitting energy means higher energy light is absorbed during DD transitions, producing a different color. Both complexes remain high spin D7, giving T2G5, EG2, and paramagnetic because the increase in splitting energy is not sufficient to overcome the electrons' pairing energy. In conclusion, MOT explains why hexaamine cobalt has a stronger ligand field and a larger octahedral splitting energy than hexaaquacobalt through stronger orbital overlap and sigma bonding. This complements crystal field theory in explaining the properties of the complexes.
I will now continue our presentation by comparing the two coordination complexes, COH2O62+ and CONH62+, using the results obtained from crystal field theory and molecular orbital theory. From the comparison table, we can see that both complexes have several similarities. They contain the same central metal ion, which is cobalt 2, so both have an oxidation state of positive 2 and a D7 electronic configuration. In addition, both complexes have an octahedral geometry with a coordination number of 6. However, the main difference lies in the nature of their ligands. Water is classified as a weak field ligand, whereas ammonia is a stronger field ligand and a stronger sigma donor. Because of this, the interaction between ammonia and the cobalt ion is stronger than that between the water and cobalt. As a result, CONH362 plus has a larger crystal field splitting energy compared to COH2O62 plus. This larger energy gap means that more energy is required for electrons to undergo d transitions. Consequently, the two complexes will absorb different wavelengths of visible light, giving rise to their different observed colors. Although the ligand strengths are different, both complexes will remain to have high spin. This is because the larger crystal field splitting energy produced by ammonia is still not sufficient to overcome the electron pairing energy for CO2 plus, which has a D7 electronic configuration. Therefore, in both complexes, the electrons will continue to occupy the higher energy EG orbitals before pairing occurs. Since both complexes have 3 unpaired electrons, they are both paramagnetic. Their magnetic behavior is therefore essentially the same, although CONH362 plus possesses stronger metal ligand bonding and higher overall stability due to its stronger ligand field. In conclusion, both coordination complexes have the same central metal ion, oxidation state, and electronic configuration, but the difference in ligand strength leads to important difference in their properties. Crystal field theory successfully predicts the electronic arrangement, spin state, and magnetic behavior of the complexes, while molecular orbital theory explains the origin of these differences through orbital overlap and bonding interactions. Therefore, using both theories together provides a more complete understanding of how ligand strength influences the electronic structure, bonding strength, color, and overall properties of octahedral coordination complex. That's all from my group. Thank you. So now everyone, let's jump to our Q&A session. So the first question is, how did you determine the oxidation state and the electron count of the metal in each complex? So now let me explain. To determine this baseline value, we look at the net charge of the complexes and the nature of the ligands. Since water and ammonia are completely neutral molecules, they contribute zero charge. This means the entire positive 2 overall charge is directly borne by the central cobalt metal, giving us a CO2 plus cation. Next, because elemental cobalt has 27 electrons ending in 3d7-4s2, creating a positive 2 ion requires us to strip away the two outermost 4s electrons first. This leaves behind a final configuration of Ar 3d7, identifying both complexes as classic d7 electron systems.
Next, for the second question, based on the crystal field theory, how are the d electrons arranged in each complex? Both Hexaaquacobalt ion and Hexaamminecobalt ion contain cobalt 2 plus ion with 3d7 electronic configuration. According to the crystal field theory, the 5d orbitals split into 3 lower energy T2G orbital and 2 higher energy EG orbital in an octahedral field. Water is a weak ligand, whereas ammonia is strong field ligand. Therefore, Hexaamminecobalt ion has a larger crystal field splitting energy, delta O, than Hexaaquacobalt ion. However, for cobalt 2 plus ion, the increase in delta O is generally insufficient to overcome the electron pairing energy. As a result, both complex adopt high spin configuration with the 7d arrangement as T2G5 EG2.
For question 3, among the two complexes, the hexaammine-cobalt 2 ion has the larger crystal field splitting energy, and this is because ammonia is a stronger field ligand than water and produces a greater separation between the T2G and EG orbitals. The larger crystal field splitting energy means that more energy is required for the T2G EG electronic transition. Therefore, the hexaammine-cobalt 2 ion absorbs higher energy, shorter wavelength light, and because the observed color is complementary to the absorbed light, it exhibits a different color from the hexaaquacobalt 2 ion. However, even though the crystal field splitting energy is larger, it is still smaller than the pairing energy for the cobalt 2 ion, and as a result, both complexes remain high spin with the electronic configuration of T2G5 EG2. Since both complexes have the same high spin D7 configuration, each contains 3 unpaired electrons and is also paramagnetic. Since they possess the same number of unpaired electrons, neither complex is significantly more paramagnetic than the other. In conclusion, the hexaammine-cobalt 2 complex has the larger crystal field splitting energy and absorbs higher energy light, but both complexes remain high spin and paramagnetic because the crystal field splitting energy is still insufficient to overcome the pairing energy of the cobalt 2 plus ion.
Question 4. How does molecular orbital theory explain the difference between the two complexes better than CFT alone? Crystal field theory explains that ligands split the metal d orbitals into T2G and EG orbitals, but it does not explain why different ligands produce different magnitudes of splitting energy. Molecular orbital theory explains this through orbital interaction between the ligand group orbitals and the metal orbitals. In both complexes, H2O and NH3 act primarily as sigma donor ligands with negligible pi interaction. NH3 is a stronger sigma donor than H2O, so it produces stronger orbital overlap with the metal orbitals. This raises the energy of the antibonding EG orbitals more significantly while the T2G orbitals remain approximately non-bonding, resulting in a larger splitting energy in hexaammine-cobalt. The larger splitting energies requires higher energy light for DD transitions, producing a different observed color. Therefore, MOT not only describes the d orbital splitting, but also explains its origin through orbital overlap, making it a more complete model than CFT for explaining why hexaammine-cobalt has a stronger ligand field than hexaaquacobalt.
Based on both crystal field theory and molecular orbital theory, CuNH362 class has the stronger ligand field because NH3 is a stronger sigma donor ligand than H2O. This produces a larger crystal field splitting energy and stronger metal ligand bonding. Although both complexes remain high spin D7 and are paramagnetic with 3 unpaired electrons, the NH3 complex has stronger cobalt nitrogen bonds, greater stability, and is more likely to become low spin than H2O complex. Since both complexes have 3 unpaired electrons, they are both paramagnetic, so neither is significantly more paramagnetic than the other. From the molecular orbital theory perspective, ammonia forms stronger orbital overlap with the cobalt ion than water. This stronger overlap increases splitting energy, strengthens the cobalt nitrogen bonds, and makes CuNH362 plus more stable. Therefore, MOT provides a deeper explanation of the bonding than crystal field theory alone.